Hello, and welcome to Particle Measuring Systems webinar titled Monitoring Guidelines for the Control of Particle Contamination in High Purity Process Chemicals. This 30-minute discussion will provide insight for particle monitoring strategies that follow the path of the chemical from tanker delivery to point of use in the fab. The presentation will begin shortly, but there's a few housekeeping items I would like to discuss first. My name is Jerry Krumala, and I'm the General Manager for the Electronics Division for Particle Measuring Systems, and I will be the moderator for today's presentation. If you have any questions during the discussion, please submit them, and we'll leave about 10 minutes at the end of the webinar to provide answers. If we happen to run out of time before completing the Q&A, the presenters will answer the remaining questions by email. Please make a note that this presentation will be posted to our website within 48 hours for future download, and you will also receive a follow-up email with a link to the recording. I would like to introduce our first presenter, David Green. David has an extensive background in particle physics and has worked with particle measuring systems for 12 years. He is currently an applications engineer for the company based out of Dresden, Germany. Our second speaker is Dwight Beal. Dwight has been with particle measuring systems for 39 years with a background in engineering and marketing. He is currently the liquids product line manager for particle measuring systems. I will now turn over the discussion to David.
Thanks, Jerry, and thanks to everybody for attending our webinar today. During this webinar, we're going to cover a range of use cases where we have had success applying particle monitoring at 20 nanometers in various applications, including testing the effects of transportation on chemical cleanliness. So this is measuring the amount of particles added to the process chemical from the shipping containers that they're transported in. Protection of the semiconductor manufacturing process through filtration and the timed usability for new, or the cleanup time for new liquid filters after installation. And we'll cover also some options for point of use monitoring for process tools and the benefits of doing so. So to start with a brief introduction, and for the most advanced semiconductor manufacturing nodes, the critical particle size is already smaller than 10 nanometers. So that means particles smaller than 10 nanometers compose a real threat to the manufacturing process. So in order to protect yield, it is important to be able to detect and control particles at this critical particle size. And traditional chemical particle counters have lagged behind the industry requirements for some time in terms of sensitivity, with sensitivity being limited to 30 to 50 or even larger nanometer particle sizes. The Chem 20 offers sensitivity for particles as small as 20 nanometers in all of the most common process chemicals, and this sensitivity is extended to 9 nanometers in the case of metallic particles. And we have already seen value demonstrated of monitoring at 20 nanometers in many aspects of the microelectronics industry, including chemical suppliers, semiconductor manufacturers, process tools, and component suppliers. And we will cover some of these applications during the webinar. So to start with, this is the testing of outgoing chemical batches at a chemical supplier. And in the example here, the Chem 20 is being used to measure the particle levels in the chemical as it is being loaded into the shipping container, which in this case is an ISO tank container on the back of a tanker. So the measurement is being made while the tanker is being filled, so we will refer to this as the fill test. And this should be one of the cleanest possible sample locations because it's after all the various stages of filtration and immediately before the chemical goes into the shipping container. Next is the post-fill test. This is performed after the fill test is complete. So the supply valve is shut off, and then a small sample of chemical is pumped back out of the shipping container and through the Chem 20 for the post-fill measurement. And this allows the cleanliness of different shipping containers to be evaluated and compared, and should also give a more representative measurement of what the particle concentration in the chemical batch will be when it arrives at the end user, or it may be tested again as part of their acceptance criteria. So this is good information to have. And the results are shown here for 9 tankers tested during loading. The solid bars on the bar chart show the particle counts in the chemical while it's being loaded during the fill test for each particle size. And the striped bars show the increase in the particle counts for each measured during the post-fill test. And overall, we found the results were broadly consistent, but there were two clear outliers identified. Tanker A, which already had a suspected contamination issue, and the results here confirm this. So we see during the fill test, the particle concentration in the chemical going into the tanker was within the normal range, but we see elevated particle counts in the chemical coming out of the tanker. So this confirms this tanker had a contamination issue that needed to be addressed in order to ensure the chemical was as clean as possible when it's delivered to the end user. Now, tanker B, in this case, we saw elevated particle counts during the fill test, and this was believed to be caused by a badly functioning valve upstream from the Chem 20 that was releasing lots of particle contamination and contaminated the fill test measurement. But overall, we found the post-fill particle counts were consistently higher than the fill tests, with an average increase of around 110% in the particle counts at 20 nanometers. So this example shows how the particle counts can be monitored at 20 nanometers during tanker loading for the COA, and the post-fill measurements demonstrate also the importance of the container cleanliness and the role that container cleanliness will play on the cleanliness of the batch when it arrives at the end user. So moving on to the next use case, this is at the opposite side of the supply chain and the testing of incoming chemical deliveries at the semiconductor facility. And in general, the particle levels in incoming chemical deliveries will be checked before they are unloaded into the facility. And this is to avoid accepting highly contaminated batches into the facility where the filtration may not be able to clean them up sufficiently. And if the chemical batches then need to be disposed of, this can be quite difficult and work out quite expensive. So the example here shows the Chem 20 being used to test chemical deliveries immediately before unloading into the semiconductor fab. And first of all, the chemical is pumped out of the tanker through the connection module into an intermediate buffer tank. And the purpose of the buffer tank is to isolate the particle measurement from the large pressure pulsations generated by the diaphragm pumps in the connection module. So basically, the chemical is pumped out of the tanker through the connection module into the intermediate buffer tank. And then the buffer tank is sealed off and pressurized slightly with nitrogen gas with just high enough pressure in order to push the chemical through the particle counter for the particle measurement. And the results are shown here for two chemical batches arriving from two different chemical suppliers over a period of several weeks. And the red bars show the average particle counts in two batches delivered from supplier A. The blue bars show the average particle counts in two batches delivered from supplier B. And we can see straight away there is a clear and significant difference in the cleanliness of the chemicals from these two suppliers. On this slide, I have plotted the average delta. So this is the average increase in the particle counts in the chemical delivered from supplier A compared to supplier B for different particle sizes. And if we look at the 20 nanometer delta, we see that supplier A was 700% more contaminated than supplier B at this particle size. And this delta decreases significantly as we go towards larger particle sizes. And at 100 nanometers, the difference is only 16%, which is not a significant difference for this kind of particle measurement and may actually be overlooked. So this data shows how chemical batches that appear very clean when you're looking at large particle sizes may in fact be very different when you move towards smaller particle sizes, such as 20 nanometers. So this shows that particle monitoring and the COA should be performed at the smallest size of concern for your process. So you cannot measure, for example, at 100 nanometers and assume because the chemical appears clean at this size, it will also be clean at 20 nanometers. Next, another semiconductor fab use case is monitoring from within the chemical distribution module. And chemical distribution modules are responsible for dispensing process chemicals to the various points of use around the facility. And at the point of use, the chemical will often come into contact with wafers, masks, and other critical surfaces. So it's important that the chemical is as particle-free as possible. The example here shows the Chem20 being used to make measurements from within a CDM immediately upstream and downstream of a final 2 nanometer filter just before the chemical is dispensed to the POU. So when the chemical batches arrive, they are unloaded first into the circulating tank and then circulated through a first stage of filtration at 2 nanometers. Then the chemical is transferred into the various day tanks, which we have 3 here, tanks A, B, and C, and then transferred to the CDM, where it's filtered again at 2 nanometers before being dispatched to the point of use. And this testing was repeated after the delivery of 4 batches. So the upstream particle counts at 20 nanometers are shown by the red bars, and the downstream particle counts are shown by the blue bars. And we found that overall the measurements were very close together, with the exception of batch 1, where we saw much higher particle counts in the incoming chemical that is arriving at the CDM. And there are many possible causes for this. It could have been a dirty batch delivery or contamination coming from somewhere within the circulating system, or possibly a problem with the filtration. And in this case, it was believed that the high particle counts were caused by a contaminated batch delivery. But the upstream measurement was able to catch the elevated particle counts in the incoming liquid arriving into the CDM. And the downstream measurements show that although the particle counts in the chemical arriving in the CDM were much higher than normal, the final stage of filtration was doing a good job reducing the particle counts back to typical levels, so it wasn't a threat to the production process. Next, so filter wetting before installation for production in the semiconductor fab. Now, particle filtration is the most important tool used to control particle contamination in chemicals and all other fluids. And particle filter performance will tend to degrade over time due to factors such as membrane wear and tear, particle accumulation, and filter fouling. So filters should be replaced periodically in order to maintain optimal filter performance. And new filters will require wetting before they can be used, which typically involves filling the filter with some kind of low surface tension fluid, such as IPA, in order to pre-wet the membranes, and then flushing with something like UPW in order to remove the wetting fluid and any residual particles that may be inside the filter, which for a brand new filter can be very significant. So some facilities will have dedicated filter wetting machines where brand new filters can be installed and flushed with UPW before they are taken out and then used in production. And the Chem20 has been used with such a tool to measure the particle concentration in the UPW while brand new filters are being flushed. And the cleanup curves are shown here for 2 different filters rated at 15 nanometers and 2 nanometers. The 15 nanometer filter cleanup curve is shown on the left-hand side. And we can see this is the particle counts plotted against the time in hours. And we can see the filter cleans up gradually to a baseline particle level around 5 to 10 particles per milliliter at 20 nanometers. And it takes quite a substantial amount of time to fully clean up. It's probably open to interpretation, but something like 24 hours. And on the right, we see the cleanup curve for the 2 nanometer filter. This one cleaned up to a lower baseline level, which you'd expect due to the 2 nanometer rating. And in the end, this was less than 1 particle per milliliter. And again, it took a very long time for it to fully clean up, probably something like 12 hours. So this use case shows how real-time particle data can be used to evaluate the proper cleanup time for new filters before they are used in production. So you can be confident the filters are fully clean, but you're not wasting time flushing the filters for much longer than necessary. Next, onto the mask blank manufacturer and monitoring from the mask blank cleaning tool. Now, photo masks are basically templates used in lithography to transfer minute circuit patterns onto wafers during semiconductor manufacturing. And mask blanks serve as the templates for photo masks. And any defects on the photomask, such as particle contamination, will cause irregularities to be printed onto each and every wafer. So preventing defects on the photomask is critical in order to maintain the integrity of the final circuit patterns and the functionality of the device. So mask blanks will be cleaned post-manufacture to remove any contamination before they're processed into photomasks. And the example here shows the Chem20 being used with a mask cleaning tool to test the fluid immediately before it is dispensed into the cleaning tank. And this test was actually repeated before and after the installation of the final point of use filter shown in the schematic here. So testing was performed first of all without the filter and then repeated again after the installation of this filter. And the results are shown here for two different cleaning fluids, UPW and potassium hydroxide, or KOH. So the dark blue bars on the left show the particle counts in the UPW before the installation of this filter. And the light blue bars show the particle counts in the UPW after the installation of the filter. And this result was somewhat unexpected because the particle counts after the installation of the filter were higher than before the filter. And this is most likely because the UPW was already very clean with particle counts around 10 particles per milliliter. And it's likely that additional particles would have been introduced into the system during the installation of the filter and possibly also from the filter itself. And since the baseline particle levels were so low, these additional particles have a more noticeable effect on the final particle concentration. On the other hand, the KOH, the results are more as we would have expected. So the bright red bar shows the particle counts before the installation of the filter, and the light red or pink bar shows the particle counts after the installation of the filter. And we see a clear 1 order of magnitude drop in particle concentration as a result of installing this filter. So the data shows that although there was no benefit to the cleaning tool after installing the filter for UPW, there was a clear benefit seen when using KOH as the cleaning fluid. Now onto the process tool manufacturer and process tool qualification. And the wet process tools are used throughout semiconductor manufacturing for many applications, including cleaning, etching, plating, and developing. And they tend to be quite complex tools that contain many components that can act as particle traps, such as process chambers, and particle sources, such as pumps and valves. And they may also have very large internal surface areas that come into contact with fluids, which can significantly increase the cleanup time when they're being flushed after manufacture. So the example here shows the Chem20 being used for the qualification of a wet process tool at a tool manufacturer. And the Chem20 is sampling from two sample locations. Sample location 1 is at the inlet of the tool immediately after the chemical is filtered to 5 nanometers. So this provides the baseline particle level. And then another measurement is performed at sample location 2, close to the outlet of the tool or the drain. And the difference between the measurement at these 2 points tells you how many particles are added to the chemical by the process tool. The results here for the 2 sample points are shown after 10 hours of flushing. So sample point 1 is the red bar. This is the incoming fluid, the baseline particle levels. The sample point 2 is the particle levels measured at the drain. And we can see that even after 10 hours of flushing, there is still 4 orders of magnitude more particles in the outgoing fluid than in the incoming fluid, which tells us that the tool is still adding significant particle concentration contamination to the chemical. So this tool would be flushed for even longer until the particle levels decrease to a level that is acceptable for the COA. And this flushing duration is unknown because it will depend on the tool and the cleanness of the tool. So real-time particle data enables the determination of the optimal flushing duration, similar to the example we covered already with filter flushing. So it enables us to determine the optimal flushing duration in order to achieve an acceptable cleanliness level without flushing it for an unnecessarily long period of time. So next, process tool troubleshooting. And if you have a highly contaminating tool releasing lots of particle contamination, then it's not good for the manufacturing process. So the ability to identify and troubleshoot highly contaminating tools is very useful to have. And the example here shows the Chem 20 being used to compare the cleanliness of coater and developer tracks at a tool manufacturer. And in this case, the chemical is a proprietary photoresist thinning agent filtered to 5 nanometers that is passed through the tool, and the Chem 20 is sampling from the point of use at the chemical dispensing nozzle. And these tests were repeated sequentially from multiple different tracks. And at the same time, offline SP5 wafer inspection analysis was performed in parallel in order to show the correlation or the difference between the two technologies. The results are shown here for two different tracks, track A and track B. The red bars show the Chem 20 particle measurements at 20 nanometers, and the blue bars show the SP5 wafer inspection results. And we found that track B was significantly more contaminated than track A with both measurement results. And this was found after some troubleshooting to be caused by an aging manifold block in track B. So this manifold block was replaced and the particle counts were repeated, and we saw a 90% drop in the particle counts after replacing the manifold. So although that there is a difference between the particle counts measured with the Chem 20 and SP5 wafer inspection analysis, the results are very good and they increase and decrease in the same proportion. So this shows how real-time particle data can be used for the most efficient identification and troubleshooting of highly contaminating tools and components. So to sum up, the use cases presented in this webinar show some successful applications of 20 nanometer particle monitoring in various branches of the microelectronic industry for several applications, including outgoing and incoming chemical batch verifications, filter performance evaluations, and tool cleanliness evaluation and troubleshooting. And as the critical particle size for semiconductor manufacturing becomes smaller in future, the cleanliness of the chemicals used in their manufacture will become even more important. And the Chem 20 allows the real-time detection of particles as close to the critical particle size as possible.
Thank you, David, for presenting all of that very valuable information to our audience today. Just to kind of go over again, we were talking a little bit about semiconductor operations and chemical process packaging, the different places where you can be monitoring there. So there'd be incoming quality measurements and online monitoring of the distribution and blending systems. You can monitor the chemical filtration and recirculation. In the process and packaging, you can qualify the chemical filters and the components, but importantly, you can do inline testing of the packaging system as well as outgoing chemical qualification testing. So these are the things that David has covered in good detail with some examples for you to cover. Go ahead to the next slide, David. When monitoring fluids at 20 nanometers, it's also important to remember the ultra-pure water process, because this comes into contact with the wafer as well as being used for diluting and blending the chemicals before processing. So at 20 nanometers, we are the leader in monitoring for both water and chemicals at 20 nanometers. Next slide, David. So again, just to kind of summarize the Chem 20 that we've talked about a lot today, it's 20 nanometer particle measurement in chemicals. We do 20 nanometer PSL calibrations with this instrument, which is the traditional calibration method. But when it comes to things like metallic particles, there is much more light scattered, and so we have sensitivity down to 9 nanometers on those kinds of particles. Gives us the ability to detect yield limiting particles that are not possible with other lesser technologies. And you can use this technology then to optimize your chemical delivery system from the loading dock to the point of process. You can improve your sample population statistics because there are typically more particles at 20 nanometers than any of the larger sizes, and gives you better, tighter process control. And more importantly, you can measure what your fab customers measure at 20 nanometers. Thank you very much for attending. You can send any questions to David Green at dgreen@pmeasuring.com. You can learn more about the Chem 20 particle counter at pmeasuring.com, or you can get a quote from your local sales representative or from our website, pmeasuring.com. Thank you again for your attention.
Okay, thanks, Dwight and David. We've got some questions that have come in from the audience. Dave, this first question is directed to you. When flushing filters after wetting, can we just measure the cleanup time for one filter and use this as the basis for future filter flushing?
It may be sufficient to give you an approximate idea of how long the filter flushing may take, but the cleanliness of filters is likely to be quite variable. So in order to be absolutely certain and have confidence that the filter is sufficiently clean before it's used in production, it would be highly recommended to measure the cleanup curve for each individual filter.
Okay, makes sense. And then Dave, there's one additional question, which asks, we need to test incoming chemical deliveries for particles, but our chemicals are delivered in drums rather than tankers. Would it still be possible to use the Chem 20 to do this?
Well, the Chem 20 requires a pressurized chemical source. So if it was possible to pressurize the drums, then in principle it would be possible. But a more suitable solution would be to use the SLS 20, which is our batch sampling version of the Chem 20. It has identical sensitivity to the Chem 20, but it's in a batch sampling offline configuration.
Okay, that makes sense. Dwight, the question has come directed to you. In one of the slides, we talked about showing multiple locations in a single chemical loop. The question is, do we really think that anyone will monitor all of those different locations? Alternatively, which locations do we think are actually the most critical to monitor?
Thank you, Jerry. Those are very good kind of questions. No, we don't expect everybody to monitor all of the locations in the fab, in those diagrams. It'd be nice, obviously. We'd be happy to help you out with that, but the typical locations that people are going to measure are going to be, at the location where the chemical comes into the factory, sort of in this case, we were talking about where the tanker lorry is being unloaded into the storage tank. So you want to measure there to make sure that the chemical is really clean coming in. And then typically the location where the chemical goes out to the fab. And that gives you the ability to know that, between the storage tanker and the point that it's being delivered to the fab, all of those portions of the tool are working, and the chemical going into the fab is as good as you would like it to be. The secondary place that people consider monitoring would be the location where the chemical comes back from the fab, because that way they would be able to be alerted to the possibility that some tool in the fab or some mismatch in the balancing of the pressures and the deliveries and everything is causing contamination to the chemical traveling past many of the other tools. And so that might be causing the chemical being filled into one of the other process tools to be getting contaminated chemical. So those would be the three primary places that I would think most people would monitor, and then they would use the other places as places to look for contamination if there is a problem in the other locations.
Okay, that makes sense. And then finally, Dwight, for you, if most fluids have a particle size distribution, then why do we think monitoring at 20 nanometers is so important? Can we just monitor at a larger size and extrapolate to what the particle levels may be at smaller sizes?
Yeah, that's something that's been done in the past when there was nothing available down at 20 nanometers, and many of the chemicals were being monitored at 30, 40, or 60 nanometers or something like that. And so they would try to extrapolate down. What we've learned since we started using the Chem 20 in some of these applications is that there can be some things happening within the system that is fairly specific about the size particle contamination that occurs. There have been cases where there have been pinholes in the chemical lining of the tank, and these generate predominantly particles in the 20 to 30 nanometer range at this particular situation and this particular customer. And so if that were the case, if you were monitoring at a larger size, you just simply wouldn't even know that it was happening, although they were very clear that it was happening on their wafers. And so you'd have this mismatch of, it seems like the chemical's good, but the wafers are having a yield problem. And so really, unless you're getting down to the level that really matters to you, there's going to be differences that you won't be able to notice. And I think in David's slide on the filter wetting, I think it was the wetting slide where we showed, there's a 700x difference between, 700% difference between 100 nanometers and 20. If you really look at that, there's probably, as at the other sizes in between, there's still differences, and the distribution may not necessarily follow the predictable pattern all the time. So in general, we feel that it's best to be monitoring as small as you can for your particular process.
Okay, that makes sense, Dwight. Well, that wraps up the webinar for today. I would like to thank everybody for attending. If we're unable to answer questions that you may have, please let us know. You can send those directly to the presenters, Dwight Beal and David Green, and we'll be happy to assist you at any time. Thank you for attending.